Okay, so the topic of today's lecture, of course, is quite different to that. We're looking at groundwater surface water interaction primarily, and we're going to start talking about the hydrograph. If we get to where I would like to be at the end of this lecture, we will get to where we should be when you start Lab 4. So you've already started Lab 4, so in some ways you're already a little bit ahead, but that's great. What we'll talk about at the end will really just be a little bit of revision of Lab 4. I'm not going to introduce anything new. I think Linda's probably gone through everything that you need to go through, but hopefully whatever slides I present will just reinforce those concepts. And if there are any questions on that, there might be some time for that in today's lecture or maybe on Wednesday's lecture. I just want to make sure that the concepts are clear as you work through Lab 4. But anyway, we want to finish off groundwater and get into surface interaction and the hydrograph, because that will provide the context for recession analysis. That'll help us understand the underlying concepts and physical processes. So on Moodle, I've posted a paper, but Steph Kienzl, of course, my colleague, someone you all know, published a few years ago. So that also reinforces recession analysis concepts. A lot of the material that's in Lab 4 for background and that I have in the lecture comes from this textbook, the Hendricks textbook that I've listed in the outline. It's not required reading material, but just for the record, that's where a lot of that material comes from, if anyone wants to refer to it. And in a general sense, the groundwater surface water interaction material is also covered in the fundamentals textbook. It's presented in a very different way, but the concepts, principles are essentially the same. Now, why did I put this photo up front? Okay, so when I was 14, I was a kid, high school. I loved the mountains, loved rivers, oceans, all kind of landscape stuff, all real fun. But I was given a physical geography project. This was in the, I think, what I would call the 4th year in high school, and you guys would call what would that be, grade 9 or grade 10 maybe. And I had an exercise. It was a hydrology exercise, and we were given a lot of latitude as to what we needed to do. And so I decided I was going to look at Dovedale in the UK. This is about 1 hour from where I lived at the time as a kid growing up. And I'd heard that this valley was quite magical in some ways. I hadn't been there before, but I'd heard that the river did some really weird things. It would suddenly resurge and then disappear and then resurge again. So it was kind of like doing this along the river profile. And I just thought, well, this sounded quite fascinating. So I just went up there to explore. And that was the subject of my class project. And I think it was this project that really led to me ultimately becoming very interested in hydrology, because it illustrated that these rivers and the hydrological processes can be quite weird and wonderful sometimes. Now, of course, the reason for this was because it was a karst environment, and you had water basically draining in the subterranean karst flow pathways, and then they would intersect with the river. And you could see this as you walked along the river. It's pretty interesting. Now, so here we can see that river valley. This is Dovedale. If ever any of you are in the UK and you get a chance, it's quite a pretty area to visit. And so here we are up on the kind of the upper, either side of the valley. We're up on, not on the terraces, we're up on the hillsides, quite a ways up from the valley. And here you can see an old relict, almost like a hanging valley. It's not a hanging valley in the classical sense, like a glacial sense, but it looks like a hanging valley because we've got that kind of classical V, and then it just kind of ends, and there's no drainage below it. It just kind of ends at the edge of the valley, and we don't see any drainage pathways, no stream there. So it's obviously a relict feature of the landscape. This is not an active river or stream system anymore. And if you were pop down into the valley and see what was down there somewhere, this is the kind of feature you'd see. You see these karst caves. And I'm sure many of you have visited these kind of landscapes, so this isn't anything that's particularly groundbreaking. That see karst every now and again in various locations. It's interesting, it's weird and wonderful. But this also illustrates that at some point we had drainage through this system. And of course, this is probably tens to hundreds of thousands of years dormant. It's not an active drainage mechanism anymore. And so, because now a lot of the karst drainage is actually even further, even beneath the river system. So it's, this landscape has evolved over hundreds of thousands of years, possibly millions of years. And so it's, you've got all these relict drainage pathways. So that's karst, something we're probably familiar with. It's not a major topic of this class, but we're at least familiar with this notion that water can drain through karst passageways, and it's going to encounter the surface at some times, and sometimes water will drain from the surface into these passages. And a great example of this in Canada, well, there's many of them, a lot in BC, for example, in the mountains, and in Alberta in the mountains, and a few places too. But one of the greatest examples in Canada is the Nahanni Labyrinth karst. Not an easy place to get to. It's in the Nahanni National Park area. I've flown over there a few times myself. It's stunningly beautiful. This is a LiDAR survey that I conducted over there a few years ago. And you can kind of see in the kind of broken up nature of the landscape here, you've got a lot of fractures. And this is all bedrock. And you can see this kind of layering in the bedrock. And these are the karst passageways. And so you've got a lot of resurgences and groundwater, surface water exchanges along here. Anyway, if ever you get a chance, it's a great place to visit. One of those places that's worth putting on the bucket list for sure. Okay, now, but of course, karst is a particular type of groundwater, surface water interaction. It's something that at one level we can intuitively understand it. It's like pipes and like urban drainage in a way. You've got flowing water going into these subterranean passages. But let's face it, that's not most of groundwater, surface water interaction. Most of the things that we deal with are going to be through soil zones and bedrock cracks, and very different type of hydrology altogether. Now, in order to understand how water moves through the soil zone, and how it's going to interact with the surface, in terms of springs and seeps and that kind of thing, we do need to start understanding a little bit about groundwater flow and how pressure sets up that flow. Now, the last lecture, 15B, is where I would really set up the concepts for this. So we're going to gloss over this extremely quickly in a couple of slides. But one thing I just want to, or where I want to start, is with these conceptions. We tend to have these intuitive conceptions that water is always going to flow from, a high area to a low area. So there's this elevational conceptualization we have that water always flows downhill, or from an area of high elevation to an area of low elevation, right? That we think we're quite intuitively okay with that idea. And then we also tend to think that water flows from a zone of high pressure to a zone of low pressure. That's something else that's somewhat intuitive, and we're okay with that. But what I'd like to argue is that these, hydrologically, these are misconceptions. I mean, yes, very often water does flow from high to low elevations, and water often does flow from high to low pressure, but not always. And so the example that you've got here is a dike in the Netherlands. Just a good example, because these illustrate quite clearly that you can have high water on one side of a dike. That high water on the dike, or earthen barrier, whatever it is going to lead to water resurgence on the other side that's going to appear to move up. So if you were standing on the other side of the dike and there's high water on the other side of it, there'll be pressure under your feet that will push the water up. And of course, as a result, in reality, in the Netherlands, they're constantly pumping water out. That you have to pump the water out because a lot of these areas are naturally below sea level. And so this dispels the myth that water always flows from high to low. It doesn't, because there's also the pressure element that you have to think of. And in this case, hydrostatic pressure pushes the water upwards because of the high water level over here. And then similarly, if we imagine a bucket, any old bucket, and you put a small hole in the bottom of it, the water pressure at the top of the bucket is lower than the water pressure at the bottom of the bucket, yet the water is still going to flow down, right? Because you're draining it. So these examples just illustrate that sometimes we have to think a little bit more deeply than these very simple conceptualizations of water flowing downhill or water flowing from high to low pressure. And so that brings us to the concepts of hydraulic head and hydraulic gradient. And it's important to understand these because this is essentially what drives the movement of water through the ground, through the ground. And so hydraulic head is the combination of elevation head and pressure head. So elevation head is just by virtue of where the water might be, relative to some datum. Could be sea level, could be some other arbitrary datum. But if one, like as you can see here in this example, we've got a water table, and so the elevation head here is higher than the elevation head here. But they're both at the water table, so the pressure head is going to be exactly the same. Now, as we go deeper into that, deeper below the water table, and the further and further below the water table we get, then the higher the pressure head will be. But here at this datum, so pressure head would be greater here than here, but the elevation head would be the same. Anyway, so if we're interested in whether there's any potential for movement from A to B, what we can do is we can look at the hydraulic gradient. And the hydraulic gradient is essentially the change in hydraulic head over distance. So delta H over L. And so in this particular case, we could conclude that water is likely to move in this direction from A to B. I mean, that's quite obvious in a way, and it's intuitive that that would be the case. But the important thing to bear in mind is you've got to separate hydraulic head into the elevation and pressure components. Now, and as I say, the previous lecture that I haven't gone through with you verbally will explain this in a lot more depth, so please refer back to those notes. Okay, now that's it for hydraulic head. very, very quickly. Let's move into how this sets up flow in the groundwater. So lines of equal hydraulic head are known as equipotential lines. Now you could think of those as being analogous to contours on a map. So, as contours represent a line joining areas of equal elevation, equipotential lines join locations of equal hydraulic head. Now, there is not going to be flow along an equipotential line because there's no difference in hydraulic head. There's no hydraulic gradient along an equipotential line. So what happens is you do get a hydraulic gradient as you travel from lines of equipotential. In the same way, if if water flows downhill on a hill slope, water will flow perpendicular to the contours. So in the same way, in the ground, water will flow perpendicular to lines of equipotential. So that's why it's convenient to think of them as analogous to contours. And so if you've got equipotential lines drawn in a cross section, then you can infer the flow direction because the flow direction is going to be perpendicular to those equipotential lines. And so you can see that on this diagram here. You don't actually see the lines of equipotential, but you do see the flow lines. And the other interesting thing to note is that where you've got changes in the soil condition or the bedrock condition, you tend to see a shift in the direction of the flow line and or the equipotential line. So you can see that here. You can see that as this equipotential line encounters sand from silt, so silt is a relatively low conductivity compared to sand, then we see that the line bends one way, and that is telling us that we've got a higher conductivity in the sand, so that water will flow more quickly through the sand. Yeah, okay, so lines of equipotential, flow lines, main thing to bear in mind just is that flow lines are perpendicular to equipotential lines, and equipotential lines are analogous to contours, but they represent points of equal hydraulic head. Okay, those are the main concepts that you need to get from that. Now, we've just looked at lines of equipotential in cross-section. We can also look at them in plan view, as if we're looking on a map. Now, of course, here's where they're going to differ to contours, because they're not representing surface elevation at all. But if we look in plan along a river stretch, the orientation of the equipotential lines are going to tell us whether or not we've got groundwater flowing into the river, or the opposite, we've got water flowing from the river into the ground. So when water flows from the river into the ground, it's known as influent seepage. And when it's the opposite, when it's flowing from the ground into the river, it's known as effluent seepage. Now, you may see these terms, you may see some other terms. So for example, influent seepage may also be known as losing flow. You might have a river reach described as losing flow. You know, the discharge is gradually decreasing. And then in this situation of effluent seepage from the ground to the river, it may be known as gaining flow. So losing and gaining are quite obvious, intuitive terms, and sometimes you'll see it referred to that. But influent and effluent are just more, I guess, more official hydrological terms, but that could also be losing and gaining. Now, as to the interaction with the equipotential lines, though, here we can see the lines of equipotential bend backwards relative to the direction of river flow, right? So this creek or river is flowing in this direction, and these equipotential lines could be described as convex relative to the direction of flow, i.e. they bend backwards, they bend uphill. And so in that situation, that tells us that the flow lines are away from the river in the downstream direction, and therefore that's going to be an influent condition. That river in this area will be losing water from the surface into the ground. Now, as we go downstream, in this example, we see that the lines of equipotential are now actually curving in the downstream direction, and that's telling us that the flow lines are into the river, and therefore it's effluent. So it's gaining discharge from the groundwater. And now, in the previous lecture, you would learn how we can observe or map out these lines of equipotential. Basically, we put nests or transects of piezometers in the ground, and from those piezometers, you could map out the lines of equipotential. So I haven't really described that in this lecture, but believe me, you can measure these things, but it does require a lot of instrumentation. So here we see a graphic stolen from the Pearson Geog3400 textbook, and we see effluent conditions. And we flip that to the opposite, influent conditions. And I guess another thing to get from this is not necessarily that this is highly vegetated and this is not vegetated, but if a river is frequently in influent conditions, i.e. it's the river has moved into a geological or soil type setting where it's generally going to be influent, well then if it's constantly losing water to the groundwater, there may not be a lot of vegetation there. A desert would be a good example. Right? You have a river running into a very sandy, arid environment, and it's losing water all the time. That's not conducive with a lot of vegetation. So that's one observation. Also, of course, as you can see here, root zones would have to be quite deep to access that water. But actually, the one thing I'd like to get from this kind of comparison is, well, there's two things really. One is that to understand that a river can go from effluent to influent in space, as a result of geological conditions or soil conditions. Okay, so that's one thing. The other thing is that the same river reach can go from influent to effluent through time. So during a drought, for example, like here on the prairies, most of our river runoff comes from the mountains. So we could have a drought here, a climatological drought. Remember a few lectures ago when we discussed the different types of droughts? So we could have a climatological drought here in the prairies, and the rivers here in the prairies could be primarily influenced. They could be like this. Whereas, of course, most of the water is coming from an area where we've got, snow melt late into the summer. And so there might not be any kind of climatological or hydrological drought in the mountains. But here downstream, most of the water is coming from an area of upstream surplus. And so, it can happen that rivers can dry up in these environments. So, yeah, and then events, of course. So we could have a scenario where the river's very low and influent, and then we get a very large rainfall event and increases the stream runoff, and then that's going to gradually change the groundwater conditions. And anyway, we'll look at that in a few slides' time. I'm starting to get ahead of myself a little bit. Actually, no, this is the slide. This is the appropriate slide. Okay, so what we've got here, let's look at the components. Where should we start? So here's our creek. Here's our groundwater table. And you'll notice in this particular case that the groundwater table is kind of curving up to the high level in the river. Well, the reason for this is this is an event. So this is a rainfall event, or could potentially be a snow melt event. But nonetheless, it's a period of relatively high flow. So the river levels, the water levels in the river are increasing, and the equilibrium between the groundwater water table and the river level has been disrupted. And so at that time, once the water level in the creek starts to go above the local groundwater table, we're going to start to see influent conditions. We're going to start to see the river lose water to the ground. And so during the event, this is frequently known as bank storage. So because we're starting to see water move into the ground, and it's gradually increasing the water table, but it's not increasing the water table everywhere. Obviously, we're going to see it first manifest near to the bank side. And so you can see that in this sequence here. So here's the pre-event situation where we see the water table in the ground is above the water level. And so therefore we've got effluent conditions. So we've got water level, transfer of water from the ground into the river. Then we see event water come along. So maybe it's a rainfall event from upstream. And now suddenly the water table or the water level in the creek is higher than the local water table in the ground. And so now we see a reversal. Now we're seeing water loss from the creek into the ground. So the flow lines are now reversed. And while that happens, we see this ridging in the groundwater adjacent to the bank. And so this is what's known as bank storage. Now in a flood condition, now this is an even more extreme scenario. In a flood stage, this is where we've got water levels above the entire floodplain. And now we're going to see seepage into the floodplain all the way across. And now we'll start to see bank storage even on the, a good example would be the coulees, right? So if this were the Old Man River adjacent to us, we can imagine this would be the floodplain, and then now we'd start to see bank storage entering into the coulees, which would be very rare, but that could happen in a flood situation. Anyway, this term bank storage is important because as the event waters rise, water goes into temporary storage. Then as they recede, we're going to see the reverse. We're going to see those temporarily stored waters in the bank are gradually, slowly going to enter back into the river. And so these processes of exchange with the groundwater in the bank environment lead to kind of moderate the hydrograph. Anyway, that's important because we're going to look at the hydrograph in a few minutes. Yeah, okay. So this is the last slide I have on surface groundwater interaction. We've mostly dealt with soil type properties, but it's very important to bear in mind that not all flow is matrix flow in a homogeneous soil medium. Groundwater zone can be quite complicated. We've got different bedrock environments. So karst, of course, we've discussed a little bit. Certain igneous metamorphic rocks are going to have lots of fractures and their own kind of bedding structures associated with them that'll lead to preferential flow. And sometimes if you've got faults and fractures in the bedrock, you'll see springs associated with them that act as preferential flow pathways to the surface. And then, of course, where you've got two different types of parent material interfacing with each other, so you can see have some kind of height vertical stratification, such as we see here. We might see springs along those beds. So we often see this on valley sides, for example, where you've got differences in bedrock geology or differences in deposits. Like you might have on the edge of a valley, for example, in the mountains, you might have a lot of talus, and then the talus just kind of stops at the valley, and then you've got silts or clays on the valley floor. But where the talus meets those silts and clays that have been deposited over thousands of years, you go from a very high conductivity zone in the talus, right, because you've got big pore spaces between the rocks, to a very low conductivity zone on the valley floor because you've got clays and silts there. So where you have this boundary in the different parent materials, you go from high conductivity to low conductivity, and so you see seeps. Now, if we had done our field trip out to Castle, I could have shown you some of these things, because around West Castle, we actually do see that. On the valley sides, we've got areas of high conductivity talus and other deposits, and in the valley floor, we've got low conductivity silts and clays, and we do see this. There's many seeps around the edge of the valley. But that's not unique to Castle. You often see that in mountainous environments. It's quite common. So the next time you're walking along the edge of a terrace in the mountains, see if you can see these. And if you can, it's probably because of the transition from high conductivity valley slope materials to low conductivity valley floor materials. You see that quite a lot. And then similarly, any kind of boundary where you've got faulting in the landscape, you might see those as preferential flow pathways leading to springs and seeps as well. So I'm pretty confident you all know what a hydrograph is. We've discussed hydrographs in an implicit sense many times already, and that's because it is something we're probably all familiar with to some degree, but maybe we haven't really broken down the hydrograph into its component parts, and so that's what we're going to try to do now. Another thing to bear in mind is that hydrographs, or the theory underlying hydrographs, may have a lot of concepts and terms associated with it, but they're all based on assumptions. They're all kind of idealizations of reality. Reality is usually a lot more complex and messy than our hydrograph assumptions would have us believe, but they are convenient. Like, for example, you can see one representation of the component parts to a hydrograph, but there's probably very few events on Earth that would precisely conform to this particular breakdown. But nonetheless, it's convenient. So this is a rainfall event hydrograph. So we've got, could be 3 hours, could be 3 minutes, but whatever it is, we've got 3 units of rainfall here. Through time, slightly different amplitudes of rainfall. So this is what's known as a rainfall hyetograph. And then following that rainfall hyetograph, we have the runoff or the stream discharge hydrograph. So it's logical, of course, that the hydrograph would follow the hyetograph in time, because the hydrograph is the culmination of the rainfall intercepting the ground, running off the ground, and eventually making its way into the river. So clearly, from a temporal perspective, the hydrograph has to follow the hyetograph. Okay, that's not a strange concept. That, I think, is fairly straightforward. Now, let's look at the component parts. So first of all, preceding the event, preceding the hydrograph, we've got base flow. So we've got these three terms here: base flow recession, base flow volume, base flow recession. Again, so leading up to the event, the river discharge should be declining in most cases. It's not always, but it should be, in theory, still receding from the last event or the last inputs into the river system. In reality, it may not, because it may be the amalgamation of lots of other events from lots of different locations, and so this is where it's complicated. But anyway, in an idealistic scenario, we would see that in the absence of any event inputs, the base flow should be receding. Then we get the input from the rainfall, so it starts to rise, and this is the rising limb. Then at some point after the event, after the rainfall, it will peak, and after that peak, we will see a falling limb. So these are just terms for the components of the hydrograph. And so this period from the peak downwards is known as quick flow recession. Different textbooks, different papers, different communities might use slightly different terms, but these are generally recognized fairly typical terms. And so later on, we're going to get to a base flow recession period again. So just like we had before the event, at some point after the event, we'll have a base flow recession period. Now, so this zone on the hydrograph is often known as quick flow. Now, what the quick flow is comprised of exactly is not necessarily that easy to determine. It could be overland flow. It could be return flow through the ground, which we haven't looked at yet, but we'll look at soon. It could be bypass flow. It could be derived from many different flow pathways and origins. But the bottom line is most rainfall runoff hydrographs are going to have this zone of quick flow. It's the period of the hydrograph that responds very quickly to rainfall. Okay. And then there's this other concept known as the time of concentration. And so that represents the time from the end of the rainfall hydrograph, so the end of rainfall input, to the end of quick flow. And so then we've got this separation point between quick flow and base flow. Now you've got to understand, this is one particular conceptualization of what a hydrograph should be. There are other types of conceptualizations, but this one's fairly universal. But the difficulty is in defining where the separation point would be. There's various mathematical ways of doing it. There's graphical ways of doing it. And we'll look at that in the next lecture. I'm not going to delve into that with much depth right now. But one thing that I think should be clear is that this notion of a separation point is a little bit subjective, right? You can see this curve. Well, where do you define this transition point is between quick flow and base flow recession? So as I say, that can be a bit of a challenge, and there are various techniques that are used to do that. But essentially what this allows us to do is separate the new event water, or the quick flow, from the base flow. And these are concepts we're going to delve into more deeply over the next few lectures. This notion of new water and old water, or event water and base flow, we're introducing them now, but I understand that they're not going to be perfectly clear. Over the next few lectures, we're going to get into this in more detail. Okay, now one of the hydrograph tools that's been around for a while is unit hydrograph analysis. It's perhaps not as popular now as it used to be, but because it's one of the original hydrograph analysis tools, I'm going to introduce it anyway. It's a useful tool to convey some concepts. And so the purpose of the unit hydrograph, or unit hydrograph analysis, is to estimate the direct runoff hydrograph from the effective rainfall hydrograph. Now, just to go back a slide, we might want to conceptualize the direct runoff hydrograph as being this quick flow part. And very often that's what you'll see. whereas the rest of it is base flow. So the unit hydrograph is defined as the direct runoff hydrograph resulting from 1 unit of effective rainfall during 1 unit of time. So in its original construct, the 1 unit of effective rainfall could be 1 inch because it was developed in the US, or it could be 1 centimeter, but it's some depth of rainfall. And then the unit time could be whatever we want it to be. It could be a minute, could be 15 minutes, half an hour, 1 hour. But very often, a unit hydrograph will be defined for something like 1 inch in 1 hour. That would be quite convenient. But we can use whatever time scale and whatever length unit we want for our particular application. Very often it's derived for 1 hour, 2 hours, 6 hours, 12 hours, or even a whole day. In order to do this, we do need to separate base flow from the direct runoff hydrograph. And so, of course, that's what we're trying to do in the last slide. So here's an example. So here's our rainfall hyetograph. Here's our hydrograph, and here's an extremely simple way to separate base flow. It is not accurate. This doesn't represent reality. However, from a mathematical or graphical standpoint, this may be a very convenient and certainly a very simple way to separate the direct runoff from the base flow, i.e. you take the discharge level immediately preceding the event. So just before the event, the hydrograph started to rise, you take the lowest discharge observed, and then you just extrapolate linearly across and you subtract everything, and then anything above that is your direct runoff hydrograph. As I say, that doesn't represent physical processes. That's not really what happens. However, it's convenient. Now, here we can see there's some reduction from the net rainfall hyetograph here. Sometimes that may be accounted for, and sometimes it may not be accounted for. Now, as I say, unit hydrograph analysis isn't hugely popular these days. It's an old technique. Now that we've got more sophisticated hydrological modeling and more sophisticated computational capability, we don't tend to resort to unit hydrograph techniques. However, this concept of net effective rainfall is important, because what that means is the shaded part of the hyetograph is the amount of the rainfall that we expect to contribute to the hydrograph. Whereas this component are the losses. These could be losses to interception storage, evaporation during the event, surface ponding on the ground. So that's rainfall that falls and encounters the Earth's surface, but it doesn't make it into the hydrograph or into a stream discharge, because it's either held in temporary storage or it's lost to evaporation. So that's why this notion of the net effective rainfall is valuable. Okay, so in order to perform unit hydrograph analysis, there are 3 assumptions, and they're all assumptions of proportionality, and they essentially imply that basin response to rainfall is linear. However, that's not true, and since these concepts came about in the 1950s and 60s, our understanding of hydrology has advanced so much that we know these assumptions just aren't correct. However, as is often the case in hydrology, they're convenient and they allow calculations and predictions to be made quite easily. And so therefore, that's why they have been popular. So the first assumption is, well, as written here, any uniform net rainfall having a given duration will produce runoff of specific duration regardless of intensity. So what that means is, for 1 unit of rainfall in time, it doesn't matter what the amplitude or the intensity of rainfall is, but for that 1 unit of rainfall, the discharge response is always going to be the same for 1 unit time of rainfall. So even if you've got one rainfall event that lasted for 1 hour and the hydrograph response took 2 hours, then even if you had a rainfall event that had 10 times more rainfall, if it only lasted 1 hour, then the hydrograph is still only going to last 2 hours. So it's this proportionality of time. Now, again, that's not really a good assumption in reality, because if you've got a very small amount of rainfall, the likelihood is a high proportion of it's going to go into storage. You have a very high amount of rainfall, you're going to go from a situation of high infiltration to high overland flow, and that's going to change the temporal dynamics of the hydrograph. So clearly this is a gross simplification, but as I said, it's convenient. So the second assumption is that ratios of runoff equal the ratios of net rainfall intensities, provided rainfalls are of equal duration. So now, instead of dealing with the proportionality of time, now we're really dealing with the proportionality of amount. So if we have double the rainfall, we'll have double the hydrograph. Or half the rainfall, half the hydrograph. So it's this proportionality of amount. So similar to time, but now it's been applied to the quantity of rainfall. And then finally, we have the superposition or the summation of events. The hydrograph for combined events is the sum of the individual events. So i.e. the principle of superposition may be applied. So here we have 3 individual rainfall components, each of different amplitudes. So for each one of those rainfall elements on the hydrograph, we can construct an individual unit hydrograph, and then we can just add them together. And so we can recreate the overall hydrograph. So, okay, so that's unit hydrograph analysis in a nutshell. We don't tend to do that anymore for all of the reasons I've outlined. These are convenient assumptions that really don't work very well in the real world. Now, it's worth bearing in mind, one area where they tend to work better than others is in watersheds where you've got no soils, it's just bedrock. And so when it's bedrock, you know you're going to get a very, very flashy, rapid response. And whilst it's raining, you don't tend to get a huge amount of evaporation. So if you've got a rapid response, you've got no evaporation, then it makes more sense that you can relate the rainfall to the runoff very, very easily. Whereas when you've got a drainage basin that has a lot of soils, then a lot is going to depend on soil moisture storage before the event. And so the antecedent conditions are going to become very important. Okay, so we don't use this technique much anymore, but this was one of the building blocks of predictive hydrology back in the 50s and 60s. Okay, so let's start to think about base flow recession. I think with 7 minutes left, I'm not going to get too far into this. But anyway, so we've looked at various parts of the hydrograph. Here's a little bit more information. So rising limb, hydrograph, time lag, different ways of looking at the hydrograph to the previous one. The new elements we're adding in here is we've got through flow. So instead of just a base flow and a quick flow or overland flow, we've also got a through flow component. I'm not going to worry too much about what that means right now, but we often see in hydrological models that try to simulate hydrographs, they'll have a base flow component, they'll have a quick flow component, and they've often got 1 or 2 intermediate components called interflow or through flow. And the notion is that they represent different pathways, different flow pathways. So some of these flow pathways could be, representing different levels in the groundwater. So you could have, as the groundwater table increases, maybe some of that flow is being pushed out into the river. You could have another interflow that represents preferential flow pathways through the ground. And we'll look at these in a future lecture. But the point is, this notion of a through flow or interflow is intended to account for the fact that there's more than just base flow and overland flow in hydrograph. And so modern hydrological models tend to break down the flow into these various pathways. Now, and we can learn something about these flow pathways from looking at the recession curve. And so this is why recession curve analysis is actually quite valuable. This graph doesn't do it very well, but it kind of illustrates that with this through flow component, where it interfaces with the overall hydrograph, there's a break in slope. You can just see it there. As I say, it's not a perfect graph at all, but anyway. So if you see a change in the slope of the base flow recession, that is very often an indication that something is changing in the storage behavior or the flow pathway behavior as water travels from upstream or the ground surface where the rainfall encounters the watershed and the creek. Something's happening as the water is traveling towards the creek, and it alters the storage dynamics of the groundwater and surface runoff. So there's a few things we can intuitively say about the recession curve. The curve slope, so the slope of this curve is a function of the upstream storage. It's a function of flow routing, and it's a function of flow resistance. So for example, if you've got more lakes upstream, then that curve's going to flatten, right? Because you've got more storages, more opportunity for storage, and that's going to flatten the curve. And flow resistance, well, that might mean, for example, if you've got more groundwater being pushed through the system and it's in a sandy soil versus a clayey soil, then you're going to get different types of resistance. Similarly, if you've got a drainage network that is dendritic, i.e. very efficient at draining the landscape, then you might have fairly low resistance. But if you've got a more kind of parallel or deranged flow network, remember from a few lectures ago, these different kind of drainage basin properties, then flow resistance might be higher because you've got an inefficient drainage network. That will also tend to flatten the recession curve. But the bottom line is, if you've got a steep curve, then your basin response is fast. If you've got a shallow curve, then your basin response is slow. Fast response means very little storage. Slow response means a lot of storage. So this notion of storage is important, and the recession curve can tell us something about the storage properties of the watershed. You know what? Linda's gone through all of this with you on Friday, and I don't have any time, but there's just a few slides here, and they should be familiar to you from the lab because they're just lifted from the lab. But what I'll do is I'll start with these on Wednesday, and if anyone has any question about the concepts of recession analysis or about the lab, we can spend a bit of time on that on Wednesday morning. I don't want to spend too much time on it because you've still got the lab period on Friday, but I do want to make sure that you're at least familiar with the concepts and that they make sense. So that's where we'll start on Wednesday. So I don't expect any questions on the lab right now, but if anyone has any other questions for me on essays, whatever, then feel free to stick around for a few minutes. And otherwise, I'll see you all Wednesday. Thank you.